like most, okay, I think folks are back. So just to kind of review a little bit of what happened there in that activity, can someone either put in the chat or shout out, what were those red lines on this map representing?
The tectonic plate boundaries.
So those red lines are the boundaries of the tectonic plates. And what we can see is, for the most part, with some exceptions, the earthquakes are happening around the boundaries of the tectonic plates as they shift, push against each other. The size of the dot tells you the magnitude of the earthquake, and then the color has to do with how recent it was. You can see there is one little dot not on a boundary that I think is interesting. Coming from Wyoming, it's in Yellowstone, so right on that super volcano. We're fine though, that happens a lot, so don't worry about super volcanoes either. But there are other reasons you can get earthquakes, I guess. They don't only happen on the plate boundaries. So the other thing, the last part of this, and this is a little confusing, so I just wanted to review this a little bit. Here we have, again, my location versus time graph. This is that question number 5 for the earthquake in Haiti. And what did you guys think? Does this fit the model, our one layer Earth model? See a few shaking heads. No, it doesn't. And it's a little confusing to think about why, but the main idea of this is we're doing some introductory seismology. I'm throwing it at you, but this is, how we test different theories. We make a prediction. If there was one layer in the Earth, we would expect for earthquakes to travel with a constant speed through that layer. So we would think that you would feel the effects of that earthquake. You'd get a nice linear relationship between location and time because the earthquake was moving at the same speed throughout the Earth. So you'd expect this to be a really nice line. Now what we can see is that when I did this, I got some kinks. So like right here, the speed changed, and we can see a little bit more up here as well. Some of this is wiggliness, is just because it's hard to figure out when exactly these quakes are hitting because things get fuzzy. But because there are these changes in speed, because we see these kinks, that tells us that our wave is moving through a different material, and as it moves through that different material, it's traveling with a different speed. So we can see, because there are these kinks, we can start to measure, get an idea of how many layers in the Earth our wave is traveling through. So based on my funky estimations, maybe there are kind of 3-ish layers. Or we're going through the mantle, through the core, and then back through the mantle-ish. Maybe this is it's a little funky because this data is kind of hard to read, but we can see that the wave speed is changing, which is telling us there are multiple layers. There's also something called the zone of avoidance, which we can see on this map, that is where if we're traveling through, if our wave gets reflected off the boundary of different layers, there's going to be an area where that wave doesn't really reach. So earthquakes aren't felt completely uniformly around the Earth. There's going to be a place where there's kind of a shadow from those layers. So that would be another thing you would look for. We don't really see it very well in this data, but there might be an area where the magnitude of our earthquake is very, very low because we're not seeing an earthquake at that location because of the shadow from those layers of the Earth. Before we move on, does anyone have any questions about that? I know it's a little tricky, but you guys are doing science. This is getting our hands dirty. Okay. So the last thing, I kind of hinted at this already, but because we have that rotation of our core, that charged material is rotating, it acts very similar to a bar magnet, and we get a nice magnetic field protecting Earth from some of the charged particles, mostly that come from the sun. So you can kind of imagine, because of that rotating core, you can think of it just like a bar magnet with magnetic field lines surrounding the Earth, coming out through the South Pole and in through the North Pole. And I know it's a little weird, it looks backwards, but this is correct. Our South Pole, the North geographic pole is the South Pole of the bar magnet in Earth, because the north bar on your compass is pulled towards the South Pole, the South bar on the Earth. So opposites attract. So we call the North Pole because it's what the north bar on our compasses points to, but it's technically the South Pole. It's a little confusing. Don't worry too much about it. But the idea is north bars point towards the North Pole, south bars point towards the South Pole. So technically, because opposites attract, it's slightly flipped in the Earth. The other thing that's cool that I don't completely understand, and I don't think science has explained yet, is that the magnetic field of the Earth actually flips every 100,000 years or so, and we are due for a magnetic field flip. So at some point, our North Pole might become the South Pole, and the South Pole might become the North Pole. We don't really know why that happens. We don't really know when it will happen. We don't know if when it happens, the North Pole will like move and be on the equator for a while and then go over, or if it'll just flip. But we can measure in the magma, in the layers of the Earth where there's magma that has iron in it, we can see that those iron crystals are aligning with the magnetic field. So how they change over time has told us that the magnetic field does flip, and it seems like it should happen soon. This is another thing that if it does happen, probably won't really be a big deal. We'll still have a magnetic field for the most part, so shouldn't hurt Earth or life on Earth. It doesn't seem like it's hurt life on Earth before, but it does happen every few 100,000 years, I think-ish. Another cool thing that the magnetic field does is that it produces aurora. So as charged particles from the sun, so the sun puts out some electrons and other highly energetic charged particles, as those wrap around the magnetic field lines, as they stream towards Earth, they get excited and produce some really lovely lights. So for the most part, green light, we're going to talk about this more in our next section, but that green light has to do with oxygen being excited, whereas red light has to do with hydrogen being excited. So another fun effect from our magnetic field is the aurora at the North and South Pole, and occasionally other places you can see it on Earth. Okay. So I'm going to wrap up today with a little discussion of the surface of the moon. The moon has, what you might notice, there's dark areas and there's light areas. The dark areas are the maria, and those formed as the moon was cooling. Impacts from the large impacts during a period of heavy bombardment crashed into the moon's surface and caused it to melt. Sorry, eventually this video will get there. So initially the moon formed and the whole surface was molten. As things crash into it, it cools a bit, but it's still, we have a molten layer inside the moon as it cools and shrinks. And as things crash into it, while that molten layer is still fairly molten, we get these huge mare, or seas on the moon where the surface is darker because it's basalts that are slightly darker than the regolith on the moon. So the rest of the surface of the moon is covered with a lighter material that we call the regolith. The mara are made out of basalts that are slightly darker and are just from these very large impacts as the magma came up, cooled, and left this basalt layers. The moon also does, this is kind of saying there are some volcanoes on the moon. It doesn't seem to be active anymore, but right as it was still cooling, as there were still a lot of magma, we do see structures that look like volcanoes on the moon, which is cool to think about. And after these maria formed, the moon has still been impacted by smaller objects, but nothing big like those giant impacts that form the maria. So the moon has been kind of pockmarked over time by these small impact craters. Some of the most prominent ones that when you look up you might see, especially if you use binoculars to look at the moon, you might notice a very prominent one, often near the bottom, called Tycho. So most craters on the moon are named after astronomers, famous scientists. So the smaller craters have formed more recently. The big ones were formed when the interior of the moon was still liquid. So we get the Maria and the highlands, which are highly cratered. And we'll get to play around with cratering on Tuesday. Throwing big objects at Earth and other things is fun. So just to show this again, this is kind of a flattened image of the lunar surface where we can see the darker areas are those basalt Maria, the lighter areas are the highlands where there's a lot of cratering. I think this guy right here is Tycho, the Tycho crater, sorry. And we can see it's recent, we can still see kind of where the ejecta came out from that crater. But mostly we split up the surface of the moon into Maria and highlands. Maria, they're called seas. There's no water there, obviously. There is some ice on the moon, but very little. At the edges of the Maria, we can see where there have been craters that have been kind of filled in by basalt flows. So this would be a crater where while the Maria were still forming, there was an impact here that got filled by that molten material. Other craters formed after everything solidified, and you can see that they did not get filled by the molten material underneath the surface of the moon. Other impact craters, like Tycho, look kind of what we expect, kind of pockmarks. There are some impact craters on Earth. We'll talk about this again more next class. There are also some features on the moon called scarps and graben. And these are kind of areas that look similar to what plate tectonics might look like on Earth, but they are not plate tectonics. The moon doesn't have different plates, but it is slowly cooling over time, so it's kind of shrinking. And as the moon shrinks, we get these kind of places where wrinkles happen on the Earth's surface, and they form these scarps or grabens as the moon cooled and shrank, and you got wrinkles across the surface of the moon. Sorry, I have to think here for a second, sorry. There's a few theories about how the moon originally formed. The main kind of most popular theory is that the moon formed separately from Earth and then crashed into Earth. So there was something that was about the size of Mars that formed in between Earth and Mars. As all the planets were still forming, as things were still getting settled in the solar system, that Mars-ish sized object crashed into the newly formed Earth and splintered, and things recoalesced, and we ended up with two bodies, the Earth and the moon. So there was a smaller planetesimal that formed around the same time as the Earth. It got pulled into the Earth's orbit, crashed into it. There was a big explosion, and we end up with two objects, one that is the Earth and one that is the moon, smaller than the Earth. So all of these kind of bring into this idea. The fission theory is a bit weird, where we just somehow end up splitting the Earth into two things spontaneously, and I don't think that one's very popular. And we can kind of test these different theories by looking at the composition of moon rocks and trying to decide if they are the same as Earth or different than Earth. And because the moon has a slightly different composition than Earth, we think that this kind of capture, smash, and then split theory seems to be the best. So yeah, it's a giant impact theory. This is the most popular. We have our Mars-sized object slam into the Earth. And then what ends up forming is we get something that we get kind of an explosion, things rotating. As things rotate, you start getting things crashing together, sticking together, forming two large objects, one of which is the Earth and one of which is the moon. And that accounts for why they are made up of similar materials. Both have a lot of iron, both have a lot of basalt, but it also explains why the surface of the Earth and the surface of the Moon are not quite the same material, and why there are more silicates and more water in Earth and more iron and basalt type rocks on the Moon. So I guess I should start. Does anyone have any questions about, we kind of ran through that surface stuff first. We'll talk more about cratering next week, but any questions here? So I want to wrap up class with what might be my favorite video on the internet.
Hello.
So this is Patrick Stewart as one of the lunar rovers.
Everyone. My masters found I have a mechanical control abnormality. Some of my body parts will not obey their commands. The sun has fallen and the temperature is dropping so quickly. To tell you all a secret, I don't feel that sad. I was just in my own adventure story, and like every hero, I encountered a small problem. Good night, Earth. Good night, humanity. Daisy, Daisy, give me your answer too. There's a silver lining in the sky. Bonsoir, old thing, cheerio, chin chin, na-boo, toodaloo, goodbye.
So I think those were all